Hello, lovely people. Welcome back to our lecture today. Um, we are at chapter 15 now, and in this chapter, we basically trying to focus on the oscillator. In previous chapter 12, we discussed about negative feedback amplifier, right? And we focusing more on the stability, like how can we use a negative feedback circuit to provide stability. However, you also remember that positive feedback may provide instability, but using that instability of the nonlinear system, you can actually provide an oscillator. So in this series, this is part one of the series when we will discuss about the oscillation or the oscillator circuit. In this part one, we will go through some basic principle. um, the next few parts of this lecture series will be focusing on some example of a practical oscillator that you can implement. So oscillator circuit from positive feedback. Uh, so previously, as I say, we know that if you want to produce a stable circuit, you may need to implement a negative feedback circuit or a negative feedback amplifier. We also saw that when the feedback become positive, it would lead to instability. But if you're clever enough, you can leverage the nonlinear property of the positive feedback system to produce like a sine wave oscillator. So for example, I pull this circuit out from Texas Instrument website. Okay, so this is called a phase shift oscillator with a single op amp. You can see a single op amp in the center. What you can see is basically this op amp is amplifier provide provide an output. Then the output is fed back to the input, right? Uh, then what you have for the output is actually a oscillating sine wave. So let's go to the basic. The basic oscillator is very similar to your negative feedback amplifier. It consists of two main components, an amplifier, and a frequency selective network, beta. So this network basically would have a similar role with the feedback transfer function that you use in your negative feedback network, which produced a feedback voltage. Okay, for oscillator, you want to have your input voltage or your source voltage to be 0. Also, previously in negative feedback, the feedback transfer function is frequency independent. So usually you remember when we do the calculation, we just get a actual number. However, in the case of positive feedback or an oscillator, you want this network to be a frequency dependent network. So if beta now is a frequency dependent network, you will have your closed loop transfer function to be AF, and AF is frequency dependent, equal to open loop gain AS over 1 plus beta S AS. Okay, and this beta A term is your loop gain, and you can represent that as the term TS. So in the negative feedback, you know that for stable negative feedback, you have Ts to be larger than 0 or to be positive. And if Ts is positive, you can have, if the loop gain is positive, you can have the feedback signal being subtracted from the input, right? However, in positive feedback, the um, the loop gain will be negative. So if the loop gain is negative, the feedback signal now get added into the um, into the input signal. So for the case of negative feedback, usually the subtraction reduce your error voltage. However, in the case of positive feedback, your error's voltage actually increase. Therefore, when your TS get to -1, the the gain of this closed loop transfer function will get to infinity. So can you imagine? Basically, you just keep adding more and more and more and more into the error signal, which get amplified up. So when you get up to -1, AF will go to infinity. This means that if you don't have any output, if you don't have any input signal, and if you assume Vs is equal to 0, for this case you still have an existing output for a 0 input signal. This is why we can assign Vs to be 0. So at what condition that the output at what condition the output can oscillate? So we will see. So we have the term loop gain, right? So loop gain is the frequency dependence function. So if loop gain equal -1, this is the condition that allow the output to oscillate. So there will be a frequency omega naught, and this is the only frequency at which the system is allowed to oscillate. This condition is called the Barkhausen. I don't know how to pronounce this. I hope I said it correctly. Barkhausen criterion. So from this equation, we can see that two conditions must be satisfied for system to oscillate. The first condition is that the phase shift through the amplifier and the feedback network both must be a multiple of 360 degree, and also it must be an integer. Also, the magnitude of loop gain must be unity. That means the magnitude must be 1. Okay, so that's it for the first basic lecture today. Will be a short one. Next, we will cover other type of other particular example and configuration of oscillator, and one of them will be the phase shift oscillator. I'll see you guys next time. Bye.